Welcome to part 2 of our Climate Change 101 video series. If you haven't already, I highly recommend you go back and look at part 1, which was the climate fundamentals. And hopefully by the end of that, you have a good sense of what climate change means, and especially how human-caused climate change relates to and is different from historical global climate change. You know how greenhouse gases work, and you know where they're coming from, both by region and by demographic. And hopefully you have a little bit of that sense of urgency that we should all feel in the midst of any crisis. This next video, part 2, will get a little bit more on the urgent side of things. And at some points during it, you might be starting to feel that doom and gloom feeling. I'm going to be giving you that message pretty hard. Don't invest too much in that feeling. And we'll talk about those feelings, of course, in the final video. The point here is not to scare you. It's to give you a sense of what is happening and where we think we are headed, by our best knowledge. But what I really want you to focus on here is seeing the interconnections between all the climate impacts that we're going to be talking about. And I'll try to spell those out pretty carefully for you. So keep an eye out for those rather than, just the list of terrible things that are happening. So we'll look at some projections of how we try to understand future scenarios for the climate, and we'll look at impacts both in terms of local and global, and in terms of today versus middle of the century or end of this century. So I'll start you off with a scary graph. Scary because it's complicated, and if you understand it, it's scary. You'll notice these things on the right that say RCP 8.5, RCP 6, 4.5, and 2.6. RCP stands for Representative Concentration Pathway. You do not need to memorize that. It just means a scenario based on some climate models that we might go down. It's sort of the climate modeling what ifs, and it's all just put on one graph. So if you look at this top red line, this kind of darker red line, that's RCP 8.5. And that is, if we continue on business as usual, what we're doing today, that is the trajectory that our climate will take. The axis we have here is in terms of how much carbon dioxide we'll put into the atmosphere every year. And on the right, under those RCP scenarios, you'll see the temperature range in Celsius that we would expect to get to by the end of this century based on that scenario. So RCP 8.5, we don't change anything about our behavior. We will end up with a 3.2 to 5.4 degree rise in temperature Celsius. And our gigatons of CO2 per year will still be increasing by the end of this century. The two colors I want you to pay attention to right now are the red and the yellow. This middle kind of brownish gray one is just a middle of the road scenario. Doesn't really help us at this point to understand it. And this blue scenario, RCP 2.6, is pretty widely considered to be impossible. Now, if we wanted to do RCP 2.6, we needed to get our climate rears in gear a little while ago, and we missed that chance. We meaning Earth. The red is sort of worst case scenario, assuming we don't do anything worse than we are doing right now. And the yellow is sort of the more likely climate resolution scenario, kind of where if we put our best foot forward from this point on, we could probably manage to do that. So RCP 8.5 and RCP 4.5. And basically what it's telling you is how bad it's going to get, or about how bad it could get. And maybe the thing to look at are these temperature ranges. So if you've been following the UNFCCC COP conferences, which I've talked about in the last video, then you know that the UN has set a goal of getting no more than a 2 degree Celsius rise in temperature globally before we start to reverse climate change and come back down, hopefully by the end of this century. 2 degrees is sort of considered the maximum before the worst of climate feedback loops take off and we have irreversible runaway climate change, and there's not much we can do to come back from it. It's kind of a loose number. Obviously 2.0 is a little bit too round to be accurate, but it's kind of a best guess scenario that's the worst we could manage as human civilization, and still keep our civilization the way it is. The real goal is more like 1.5 degrees, because at 1.5, we managed to avert a lot of the effects of climate change, and a lot of those, especially low-lying island nations or coastal nations, won't be drowned, because at 2 degrees, we're going to lose entire countries because of sea level rise. At 1.5, we might be able to squeak by and save some of those countries. So formally 2 degrees is the goal of the UN. 1.5 degrees is the real goal. Ideally, we don't get any more than we already have, which is 1.1 degree. We're already 1.1 degree warmer than we were. So this RCP 4.5, you can see we will have already surpassed that 1.5 mark. If we wanted that 1.5 degree maximum temperature rise, we need this RCP 2.6. And again, we're just not headed that way. That's not to say we couldn't do it, but it would involve completely overturning our economy. Not to the detriment of anything in particular, but it would involve a whole lot of political will that we just don't have right now. So RCP 8.5 is where we're headed. RCP 4.5 is probably the most likely best case scenario based on current politics and policy. So there you go. That's the scary graph. This is the 2014 version. I think the latest IPCC report probably has a more updated version of this, so we can see where we are. But consistently, historically, every time one of these RCP graphs comes out, we are on or even above the worst case scenario. So we are not shifting very quickly into that yellow or blue range. This red line is also what we call a hothouse Earth scenario. If you think about the Earth's temperature, we kind of sit in this equilibrium. You know, even if a few things happen on one side or the other, the Earth will always kind of come back to this temperature equilibrium that we've had throughout the Holocene. What happens with the hothouse Earth scenario, this RCP 8.5, is that we will kind of flip out of that equilibrium and drop into a trajectory that brings us just to ever increasing temperatures, a runaway greenhouse effect that we couldn't easily reverse. And that would mean mass extinctions, greater than 50 or 60% of species on Earth would go extinct, and human habitation would be limited to just a few places around the planet, depending on technology and population. So that hothouse Earth scenario, if you hear that lingo, that's what we're trying to avoid. But this RCP scenario stuff, that's good just vocabulary to have with you. It's a great way to impress people at the bar. If you meet some climate change people there, let's talk about RCP 8.5. They'll buy you a drink. So what? Okay, so you saw this scary graph. We can see what bad temperatures look like on a graph. That's not terribly confusing or exciting. So what I want to look at today, or in this video, is what do those temperature changes manifest as? Like, how do we experience them other than just a warmer day or a slightly higher thermometer? Because if you think about it, a 1, 2, 3 degree rise in temperature doesn't seem like a lot. The temperature has changed more than that since I started this video outside. So it doesn't seem like a lot, but in terms of global ecosystems, it's a huge change. But what does that actually manifest as? What are we seeing just in terms of our observations of climate change around us? And what can we expect to see in mid-century or end of century? So I'll start with Montana, because you are all presumably in Montana. I'm in Montana. I'm looking out my window at Missoula. This is what we're expecting to see. Pretty obvious, warmer year-round temperatures. Probably could have guessed that. But that just means, on average, the temperature each year will be a little bit higher year to year. We will still see cold extremes, but we will see more heat extremes than cold extremes. So if you think of the temperature of a year as a bell curve, so most of the year we're somewhere in the 30 to 70 degree range. That would be the peak of the bell curve. And for a very small portion of the year, we're above 90 degrees. And for a very small portion of the year, we're below 0 degrees. That's kind of the bell curve I'm thinking of. We will still get very, very cold days. And we will still get very, very hot days. And every year we'll break some heat records and we'll break some cold records. And normally you would expect in a given year, you'll break the same number of heat records as you break cold records. And that's how it's always been. But as temperature is going up year to year, what we're going to see is more and more heat extremes, fewer and fewer cold extremes, even though those cold extremes will still be there. So if it's a really cold snap and someone points out the window and says, look, climate change is a hoax, you can draw a bell curve for them and say like, yeah, we're still going to have cold snaps. We're just going to have a lot more of those really hot days than we used to. Still in Montana, changing water regimes. This is going to be a big one, and I'll talk about this more in a bit. But our precipitation patterns are changing, our drought patterns are changing, and flood patterns are changing. And these are all, of course, related. And I'll show you some graphs on that in a minute. More related to the kind of things you all are going to be working on. We will get an increase in vector-borne disease potential. This is already starting. The spread of ticks, especially, is something we can measure pretty well in especially Western Montana. And so Lyme disease, Rocky Mountain spotted fever, things like that are going to become more and more prevalent. And so that alone is a challenge, but also the fact that a lot of health professionals in Montana are not trained to recognize these because it hasn't historically been a big deal here is going to be an extra hurdle to get over. We're going to have to all be trained on how to recognize these symptoms. So expect more vector-borne diseases just because of the warmer temperatures and the increase in precipitation. And then, as you well know, especially right now, if you're watching this soon after I'm recording it in August of 2021, we're going to have more wildfires and smoke. So if you remember 2017, or if you've been paying attention to the wildfire season this year in 2021, those historically would be like 20-year or 50-year fire seasons, meaning like that's the worst you would see every 20 or 50 years. That's going to become the annual norm by the middle of the century. So by 2050, maybe as soon as 2030, almost every year is going to be like 2017 or 2020 or 2021 in terms of amount of wildfire and amount of smoke. And of course, this leads to not only death and loss of property, but of course, respiratory illness. So if you want to see some more color-coded versions of this, we expect all of Montana to see more days above 90 degrees. This is one metric of climate change that we use, days above 90 degrees. And this, if you've experienced 2021, this graph might look a little silly because it's suggesting that in Western Montana, if you live out here, we might see 5 to 10 more days over 90 degrees than we used to. We've had almost 2 straight months over 90 degrees. So we've far surpassed this graph this year. But if you remember from the last video, climate is not a 1-year thing, it's a 30-year average. So this year is not proof of climate change, it's just indicative of climate change. It's illustrating kind of what is going to become the new norm. And of course, all over the state, we're going to see by the middle of this century a change in temperature 6 degrees or higher, annual average. Precipitation, we're expecting the whole state to get a little bit wetter, mostly in the form of rain. And it's not a huge amount, it's, you know, single digit percentages. But it is going to matter in a second when I show you the timing of it. And just sort of like those days over 90 degrees, another metric we use for climate change is the number of freeze-free days. And this is important because a lot of our ecosystem depends on having freezes for certain durations of time. If you think of, if you pay attention to environmental news, the beetle infestations, the invasive beetles that have been killing and drying out so many of the forests in Western Montana, those are beetles that used to be killed by having a 2-week freeze in the middle of winter, but we don't get 2-week freezes very often anymore. So those beetles don't die. So they come back every summer in greater and greater numbers, and we're losing more and more forests. So that's why that freeze-free day thing is an important metric. So these are all annual averages that I'm talking about. Where it gets, I think, much more illustrative is when we look at how this pans out over the course of a year. So let's take that temperature and precipitation thing and look at it month by month. So I already said it's going to get on average a little bit wetter and a little bit warmer across the state, or a lot of bit warmer across the state. But it's going to be concentrated. We're going to get warmer, wetter winters. and then even warmer but drier summers. So what's going to happen is we're going to get more precipitation in the winter, but it's not going to come as snow as much. It's going to come as rain. So we're going to get it either washing out, or we're going to get rain on snow events, which, as you know, can lead to avalanche and other issues. And then all of that stuff's going to run out through the rivers by the end of spring. And we're going to get less precipitation, less rain in the summer. So we're going to get all this soil runoff, loss of topsoil because of flooding in late spring, and then a super dry summer with none of that topsoil around. And so we're going to get flood conditions and then drought conditions more and more from year to year. So if you are a farmer or a rancher, or if you are in tourism, this is a huge problem. And you're looking at this and not terribly pleased with what this means for your farming or ranching operation. But this is, I think, a better illustration, a more detailed but more important way to look at climate change in Montana than just talking about annual averages. If we want to broaden out a little bit, talk about sort of countrywide, the types of things we're going to see. It's hard to get too detailed with this because every part of the country, every little microclimate and ecosystem is going to respond differently. But sort of broadly speaking, in the US, we are going to see more extreme weather events. And you've already seen this. If you watch the news, we get more hurricanes and more intense hurricanes, more tornadoes, more flooding, fire, all that stuff. Those are just going to become more likely. It's not that we can point at a hurricane or a wildfire and say, hey, that's climate change. But what we can do is point at a hurricane or wildfire and say that was more likely and is more intense because of climate change. So it's hard to just say something is climate change or not climate change. It kind of weaves its way into everything. But we are going to see more extreme weather events and more of them. One of those that you'd be familiar with is the polar vortex. And this seems a little counterintuitive because the polar vortex means, a week or two of really intense cold in a season that's already pretty cold. But what's happening is that, I'll talk about this in a minute with global issues, but the Earth is warming more at the poles than it is in the mid-latitudes and equator. And that doesn't really sound like a big issue if you're not living at the poles. But what that temperature gradient allows, having like really cold temperatures in the poles and then average temperatures in the mid-latitudes and equator, it allows for this cycle of air to just kind of perpetually move between those two pockets of air. And that happens up in the stratosphere. That's what we call the jet stream. It's this big cycle, this big wind that kind of keeps moving around, and it's kind of keeps that cold air up north and keeps the warm air down south if we're in the northern hemisphere. As that temperature gradient lessens, because the pole is warming more than the rest of the planet, that airstream starts to slow down. And if you want to think about this like riding a bike, if you ride your bike very slowly, it's hard to keep your bike straight and you kind of wobble back and forth. You might fall down. If you bike really fast, because your tires are spinning so fast, you actually are very stable. You can take your hands off the handlebars and not fall down. The same kind of physics works with this jet stream, where the more there's a temperature gradient, the faster that jet stream moves and the more stable it is. As that temperature gradient decreases, that jet stream slows down and it starts to wobble. And what happens with the polar vortex is that jet stream like wobbles down really far, farther than it normally would. And so we get that big pocket of cold air coming down, and then it'll wobble back up. If it slows down enough, it'll actually break. The stream of air will actually dissociate. And then we have other issues. But that's what the polar vortex is. Across the country, we're seeing more drought and flood conditions, sometimes in the same places, for the reason of timing that I just illustrated here in Montana. But like right now, this summer 2021, most of the Western US has been in drought. Most of the Northeast has had flooding issues. We're going to see more wildfires, largely because as you increase temperature and you decrease the hydrological regime of an area, it just dries the place out and it's more likely to catch on fire. And with more weather events, we have more lightning storms. That's more likely to start natural fires. Heat waves, that should be pretty obvious. That heat dome we had sitting over the whole Western US this summer, those aren't unheard of. That's not caused by climate change, but climate change sets up the conditions for those heat domes to be more and more likely. Coastal erosion. This is more of an issue on the East Coast, which is a shallower coast than it is on the West Coast. But as temperatures of the ocean rise and as the ocean itself rises, you get bigger and bigger storm surges. The wind is able to push more and more water onto land. And especially when you add the increased hurricanes, we're just going to get more and more water kind of lapping against the shore. And that can erode whole coastlines and property. And if you consider that something like 80% of the human population lives within 100 kilometers of the coast, that's going to mean a lot of human movement inland, not to mention the insurance costs that we're already seeing in the Southeast. So you could keep going with this list. There's lots of different climate impacts you could look at in the US, but those are some of the big ones. If we look globally, I'll try to focus on things that are just kind of global in scale. I already talked about the poles warming faster than the equator. That's what's causing that polar vortex. The oceans are where the Earth holds most of its energy. And so you think about all the energy coming in from the sun, all the carbon being stored in the atmosphere, a lot of that's actually being absorbed by the oceans. So the oceans are warming up and they're absorbing a lot of that excess carbon, and they're acidifying because of that carbon. And that is wreaking havoc on our coral reef systems and just kind of ocean ecosystems in general, especially shallow seas, which are becoming less shallow. But the oceans are kind of reaching the maximum of their capacity. They can't take a whole lot more carbon and they can't take a whole lot more heat. And so a lot of that energy is going to start spilling out into the terrestrial and tropospheric ecosystems. When I say ecological straining and breaking, that third bullet point, think about food webs or symbiotic relationships between species. Every species is going to have to adapt in its own way to climate change, specifically the rising temperatures and changing water regimes. Some species are going to move north. Some species are going to move uphill to find cooler temperatures. Some species are going to change physiologically. Others will change their diet, and others will die off. We're already in the middle of a mass extinction, so a lot of them are dying off. That's terrible for a food web. If you're one species and you prey on a different species and that species just disappears because it moved uphill and you don't know where or why, you have to find something else or you perish. And so all these webs are being strained and in some cases broken, and we're losing whole ecosystems around the world. And to wrap all this up, I want to give you a term, global weirding. This has become a common term for anyone in the climate change world because global warming is a little bit too simplistic. You know, we already talked about cold snaps, like it doesn't feel like the globe's getting warm necessarily, even though it is on average. But what we're just seeing is just weirding, like everything is getting weirder. Everything's getting more intense, weird weather, weird storms, weird ecosystem issues going on. And so if you want to break out that term in lieu of global warming or climate change, you're well within your rights to use that. It's a little bit more illustrative. So I promised I didn't want you to get stuck on just like the list of doom and gloom, all the bad things that are happening and going to happen. I would rather focus on sort of these broader considerations, these broader contexts. And instead of thinking of impacts as just one bad thing happening and then another bad thing happening, think about feedback loops and interconnections. A feedback loop is when, you know, thing A causes thing B to get worse. And by thing B getting worse, it causes thing A to get worse. And then thing A causes B to get worse. And it just keeps going round and round and round. A good example of this, the melting of ice on the surface of the Earth. And that's related to sea level rise as well. But I just want to focus on, you know, let's say the polar ice cap, that just, it's a layer of ice that floats over the North Pole. From space, that polar ice cap is just a big mirror. You know, anything light colored on the Earth is really good at reflecting light. It keeps us cool. So ice is really good at keeping the Earth cool. As the Earth warms, that polar ice cap is melting. And so we're losing that mirror. So more and more solar radiation is hitting the ocean. And if you look at the ocean from space, it's a very, very dark blue. And if you've worn a very, very dark blue t-shirt on a very sunny day, you know how warm that gets. So that dark blue color absorbs a lot of that light. And that causes the ocean to warm even more, which melts more of that ice, which causes more solar radiation to be absorbed by the ocean, which melts more ice, and so on and so forth. So that's a feedback loop where once it starts, you can't really reverse it because it sort of feeds itself. Another one is the melting of permafrost. We talked about the poles warming more than the equator. A lot of the northern hemisphere is permafrost underneath Russia, Canada, Alaska, Scandinavia. And the permafrost sits over a layer of methane. The methane is there because a lot of organisms decomposed a long time ago and then were covered by that permafrost. And so that gas, that methane that formed from the decomposition can't escape. So it's just trapped there, and it's been there for millennia. When the surface of the earth warms up, that permafrost melts. It's essentially, micro ice. And as that permafrost melts, it allows that methane to escape. And if you remember from the last video, methane is 25 times stronger than carbon dioxide at warming the climate. And so we're releasing methane into the atmosphere, which causes more global warming, which warms the permafrost, which releases more methane, which warms the climate, and so on and so on and so on. So that's another feedback loop. If you want to think of a feedback loop in terms of human behavior, as it gets hotter, we're more likely to use air conditioners. Air conditioners use electricity, which means burning coal and natural gas. And some air conditioners might use CFCs or HCFCs as a coolant. And so you're releasing more greenhouse gases into the atmosphere as a way to cool yourself down, which of course warms the climate, which means you need more air conditioning, which means you release more greenhouse gases, and so on and so on. So those are those feedback loops that we need to keep track of. And when I talked about that 2-degree limit, or the 1.5-degree limit that the UN had settled on, it's those feedback loops that we're trying to avoid, because those are irreversible. Looking at the second point, ecosystem services, this is just a good way to think about how climate change impacts you. Especially if you live in an urban center, you may not be as familiar with where your food comes from, or where your water comes from, or why your air is clean or not clean. We depend on the natural world to clean all that stuff for us. We have industries that do it, but we still depend on natural systems. If you are getting clean water out of a water table, that's because it's filtered through an ecosystem that cleaned it up for you. If you're getting your food from somewhere, even if it's a super industrial scale farm, they still depend on natural pollinators that will come every season and pollinate all their crops. So if we lose pollinators, if we lose soil bacteria, if we lose understory or overstory, we are losing ecosystem services that we depend on for our survival. So it's good to think of climate change not just in terms of a loss of a few plants or a few animals. This is a very human problem as well. And that's illustrated maybe best by human health. And I won't get into detail with this because that's what the rest of your training series is about. So you'll see a lot of that. And then the last piece that I think is worth considering is the social strain. And this is not something that we in the US really know to look for, although it is definitely is happening. But if you think about all these physical impacts added up, the loss of ecosystem services, the loss of water security, the loss of food security, increased temperature, that leads to social strain. And I'll try to illustrate that here a little bit. So this is a sort of a chart of climate impacts from a group called Climate Interactive, and they make these kind of role-playing games and simulations that you can check out to kind of see if I made these decisions, what would that result in terms of the climate. So you can see these yellow and orange arrows, for a given temperature rise across the top here. When will these impacts begin? How fast will they move? And, we've already increased the temperature of the Earth 1.1 degrees Celsius. So we are here. So we've already started these things. Small mountain glaciers disappear. We already know that. If you live close to Glacier National Park, we're losing glaciers. Rising crop yields in high latitudes. That seems like a good thing. There's kind of a double-edged sword there. Severe impacts in marginal Sahel region, so West Africa, is seeing huge issues with their food security. So these things are already in motion. We're not going to undo these. If we could keep temperature below 2 degrees, we might avoid the worst of these things. Entire regions experience major declines in crop yields. Sea level rise threatens major world cities, things like that. So you can kind of get a sense of when these impacts will begin, what kind of temperature rise would lead to these issues. But one of the most fascinating things about this chart to me is that it stops. There's just this gray area over here. And I think they did that because that's where they wanted to put their MIT label, which is great. And they have their RCP scenarios up here. So this would be, probably RCP 8.5 is the 7.4 degree rise. RCP 6 is this 5.3, something like that. So they're giving you a range of where we might end up by the end of this century if we don't do anything. But there's still this big gray area after 6-degree rise, and after all of these things have happened. We don't really know what happens after that. We can guess at physical changes to the Earth's climate and ecosystems, but in terms of human society, we don't know what happens when you strain the ecosystems and water and food and habitable land so much. And so if you think about a lot of the civil conflict that's happened even in just the past decade, Syria is actually kind of the poster child for this, unfortunately, as is Yemen. There's already civil strife, there's already political conflict, but a severe drought came through and really stoked the fire and kind of threw everything over the edge. It's kind of the straw that broke the camel's back in a lot of cases. And we're seeing these sorts of things pop up all over. And this creates human migration and refugees. And if you've been in Montana for the past 5 years, you know how hard it is to get people to even agree to resettle refugees in their state. So imagine more refugees coming because of climate change, because their country has disappeared underwater, or because it's on fire, or because food security and water insecurity have driven people to flee. We see this in Bangladesh right now. We see this in Vietnam right now. It's kind of all over the world. And so this is really the biggest piece of climate projections. What's going to happen to human society if we let things go the way they're going? And that alone is a big enough incentive to really focus on mitigating climate change, which is what we're going to talk about in the next video. So I apologize if this one was a little bit of a downer. That was intentional, but I'm going to address that in a couple videos from now. And so if you are ready, tune into the next one. We'll talk about how we mitigate climate change, and I'll see you there.